Today we are going to continue the study of electric multipoles. We are going to recall that what we actually want to do is to calculate what is the electric potential on an arbitrary point of the space P. Okay, this could maybe have coordinates x, y, z. And well, we will have an electric potential on the point P due to a distribution, a random distribution of n electric charges. In this case, for example, I wrote Q1, Q2, all the way up to Qn. So we take an arbitrary charge Qi and then calculate what is the electric potential due to this charge. And then we sum every contribution to the electric potential for every charge. Okay, we saw on that first video that, well, first of all, the general formula to calculate the electric potential due to n charges is this one over here. Okay, but we wanted to calculate the electric potential on a more accurate way, and what we saw is that we can deduce this formula that we have here, where we get three important concepts, that is the monopolar term, the dipolar term, and the quadrupolar term. Okay, remember that, well, we got these terms making 1 over Ri to be equal to 1 over R times the square root of 1 plus t, where t was defined to be Ri squared over R squared minus 2 Ri over R cosine of theta I. And then what we did is to express this function over here as a series expansion using the Taylor series expansion. And well, if we do that, we saw that we get 1 minus 1 half t plus 3 over 8t minus, this is t squared, minus 5 over 16t cubed. And what we did on that video is to take only until the term 3 over 8t squared. Okay, we made an approximation of second order. So we said that for every t cubed, t to the fourth, t to the fifth, all those terms were going to be equal to 0, so we canceled them. Okay, so what we are going to do now in this video is to mention a form that is perfect to define the electric potential but without making any cancellation. And also recall that the reason why we took t to the third power equal to 0 is that, well, we took a point P that was very far away from the charge distribution. So that makes the quotient Ri over R approximately 0. Okay, so we can cancel those terms. For example, for t to the third power, t to the fourth power, and if the power is greater, then that term will be more and more equal to 0 or close to 0. Okay, so what we want to mention right now is that, well, we have also other videos about Legendre polynomials. Okay, in those videos we saw that, for example, the 0 order Legendre polynomial P0 of x is equal to 1. Then the first Legendre polynomial, well, the Legendre polynomial for n equals to 1 is equal to x. And for example, the Legendre polynomial 2 of x is going to be equal to 1/2 times 3x squared minus 1. And well, if we find the next Legendre polynomial, P3 of x is going to be 1/2 times 5x to the third power minus x. Okay, so look that there is some similarity with the coefficients of the monopolar, dipolar, and quadrupolar term. In this case, we can write, for example, in this monopolar term, we can write that this is multiplying 1. And look here that, for example, we have here a cosine of theta I. Okay, that it will be, we're about to watch it, this will be equivalent to the x, And for example, if cosine of theta I is equal to x, then we will have here 3x squared minus 1 over 2, which is what we have here. So this will be equivalent to 3x squared minus 1 over 2. So what I want you to notice here is that we actually have the Legendre polynomials in this series expansion of the electric potential. So we can use the Legendre polynomials to define the electric potential. And look that we actually have another term that is the Ri, okay, that from here we can have Ri to the 0 power, here we have Ri to the first power, and here we have Ri to the second power. Okay, and other thing to notice is that we have a 1 over r term here, 1 over r squared here, 1 over r to the third power here. Okay, so we can express all those terms that are changing in terms of another sum. Okay, so what we are going to do first is to write the electric potential as the sum of three terms. Okay, we are going to join every term on just one sum. So this will be phi equals the sum from I equals 1 up to n of qi over 4 pi epsilon 0 r plus qi ri cosine of theta I over 4 pi epsilon 0 r squared, and then plus qi ri squared over 4 pi epsilon 0 r to the third power times 1 over 2 times 3 cosine squared of theta I minus 1. Okay, we can take a common factor here, the sum from I equals 1 up to n of, it will be qi over 4 pi epsilon 0 r times, well, it will be 1 plus ri cosine of theta I plus ri squared, and this is over r, this is over r squared, and here we will have times 1 over 2 times 3 cosine squared of theta I minus 1. Remember that this is the P0 Legendre polynomial, this is the P1 Legendre polynomial, and this is the P2 Legendre polynomial. So it seems like we have a sum of Legendre polynomials. Okay? Okay, so we are going to name the L Legendre polynomial as PL of x. In this case, remember that P sub 0 of x is equal to 1, P sub 1 of x is equal to x, and so on and so forth. Okay, so in this case we see that we need to change the x for cosine of theta I, as we mentioned before. So we have PL of cosine of theta I. Okay, so this one will be equal to P sub 0 of cosine of theta I. Okay, this cosine of theta I will be P sub 1 of cosine of theta I. Okay, 1 over 2 times 3 cosine squared of theta I minus 1 will be equal to P sub 2 of cosine of theta I. Okay, we are just switching x for cosine of theta I. Okay, so we are going to get that the electric potential is going to be equal to, well, the sum from I equals 1 up to n of qi over 4 pi epsilon 0 r times, well, we are going to have a sum of Legendre polynomials. So it will be a sum from L equals to 0 up to infinity. And I'm about to explain why infinity. Okay, of the L Legendre polynomial of cosine of theta I. Okay, and recall that, well, we have an Ri over R here that will be raised to the L power. Okay, for the first term, we see that L is equal to 0, so we get 1. In this case, L is equal to 1, so we get Ri to the 1 power over R to the 1 power, and then here we have Ri to the second power over R to the second power. So this sum matches with what we are looking for. Okay, so just let me explain that this infinity that we have here is to express the definition of the electric potential in a very accurate way. Okay, because remember that we were cutting up to the second order approximation. In this case, we are taking the sum up to infinity, so that means that we are taking into account the cube term, the fourth power term, the fifth power term, all the way up to infinity. So the Legendre polynomials allow us to define the electric potential in an exact way. Okay, so we are not making any approximation. This is actually the exact definition of the electric potential due to this discrete distribution of n charges. Okay, perfect. So this will be the important result of the video. And just let me recall that we have made another video talking about the Legendre polynomials. And in that video, we showed this formula that we have here. Just if you were wondering how to calculate Legendre polynomials, well, there are many ways, but one of these is using this recurrence relation that we showed on that video, how to get to this formula. Okay, remember that in this case, looking at, well, if you have, for example, p sub 0 of x and p sub 1 of x, well, with this formula, you can calculate every Legendre polynomial that you need. Okay, perfect. So if you have any question, just leave it on the comments.